Okay. Okay. Good morning, everybody. Thank you very much for staying here. I think that we will have a wonderful lecture today. I have the pleasure to introduce you Professor Katsuo Tsukamoto. We know each other from many years ago. He's I think the problem in the field of crystal growth is one of the best microscopy, the people who better understand growth mechanisms in nucleation and crystal growth processes. He developed a laboratory, fantastic laboratory, famous everywhere in the world, in the Tohoku University. He has been always linked to Tohoku University, right? He was the tutor was Professor Tsunagawa. He's a very famous, also crystal warrior, already passed away. And he was working always with Professor Tsunagawa. And then later, he organized the laboratory for crystal growth processes, mechanism of crystal growth processes. In this laboratory, many of the most outstanding scientists in nucleation and crystal growth were out there, and there was a former there in the Professor Tsukamoto laboratory. And for instance, Gen Sasaki, now in Hokkaido University, Yuki Kimura in Hokkaido University too, Naoko Maruyama in Osaka University. So many people, many young people now leading the most important projects in crystal growth in Japan. They were forming in the laboratory of Professor Tsukamoto. So he had, many awards in the society in Japan, in different societies in Japan, particularly the Society for Crystal Growth. Also is a member of the Japan Society for the Promotion of Science, so it's very much linked. Also, his work in microgravity experiment, with JAXA, Japan Space Agency, but also with NASA and with the European Space Agency. We were working together in this project. So he is a very well-known microgravity science. And he got the very prestigious Grand Prize of the International Organization of Crystal Growth. So for me, it's a pleasure to have here Professor Tsukamoto. I think that we will enjoy very much this lecture because, he has wonderful videos that illustrate very well the different mechanisms of formation of crystal. Please.
Okay, thank you very much, Juan. And I'm very glad to be here. First, I would like to thank Wamba and your colleague. I was invited to this city, San Sebastian, for the first time. And as Wamba said, I came to Granada many times for the last 20 years, more than 20 years. And I don't know when I met him, maybe in a small airport. I don't remember exactly. But after that, we had a very long-standing collaboration and friendship. And now, this is my first visit to this city. So today, I would like speak about this kind of topics. Of course, crystal growth takes place on the surface of the crystal. So we are interested to look at the crystal surface. And later I will say, not only crystal surface, but also the area just adjacent to the crystal surface in solutions. So solution has also crystal structures, molecular structures. We can visualize it. So first come to one's picture. Before I came to this country, I visited Delft in the Netherlands. So in a city hall, I saw a small boy was watching some small instrument, this one, very small one. So this is, and he continued to look at this one. Probably he became very much interested for 5 minutes or more than that one. I took picture. So, and this is the first microscope, optical microscope developed by Leeuwenhoek. He's very famous person. And here is a very little bit magnified one. Here is a small lens. So sample can be put here. So you can adjust. So you have very interesting result. And he is known as a person who lived in the same city in the same period, and who, I forget the name of the painter. I forget famous things. What happens? But anyhow, it's okay. And so let's start. And also several years ago, I visited Brussels. And Brussels is, Magritte. He is very good painter. And the former one, that is about microscope. That is my first talk, first half talk. And the second part is about the space. So the Japanese small satellite went to a small planet and they pick up some sample, come back to the ground. We have that sample. So, astronomy was in former times. Still now, the words in which they use microscope, telescope. But we are using microscope to understand the history of planets. So that is the second part of this. So this is very interesting, and I like this picture very much. So it seems that all the painters might have been surprisingly good at imagine what the future would like. So this is nice. And International Space Station, we can go there. We can do some microgravity experiment on that part. So anyhow, very good painters you have in Europe. And the second one, okay. So we shall think about the crystal surface. This is one of the protein crystals, and he's one of his colleagues. And when he was in Japan, in Sendai City, he took this kind of pictures, movies. And, probably everybody knows about this one. This is a crystal. We are looking at the crystal surface. And if you look at the center, you can see some spiral patterns. So this is a spiral growth pattern, we say, spiral growth. And another crystal, but here is no spiral. But here nucleation appears and they grow, birth of nucleation, and they started to grow. You can say, oh, this is very special microscope. But now you can see some terrace, some steps. The height of the step is one molecule. So in this crystal, 5 nanometer or something like that. And here maybe some similar. But we can see steps down to 5 angstrom. So half of the nanometer. So most of the crystal is good to be observed by this kind of microscope. So this is by optical microscope. And now I have no time to discuss about the principle, but you can see this is say growth hero. So it's the same as a geographic map. So these are contour lines. So you can see the difference. So normally they use this type of normal interferometry. But our interferometry much sharper and very clear. And the very important thing is, so each pixel of this one has a height phase information. So concentration or height of the steps. So therefore, we can, if you take this kind of picture, you can get the three-dimensional images. And also, the fringes are moving outwards by the growth of crystal. You can measure the growth rate exactly. But in normal way, you have to measure how much this fringe will be bent. So that is a way. That is not so sensitive. So therefore, we can say this is 100 times more sensitive. Phase shift interferometry is a very, very, how to say, sensitive way. So here is one example. The surface of lysozyme, one of the protein crystals, and yeah, you can see. So islands with one molecular height start to develop. New one appears somewhere around here. So this is not a micrograph. This is not a micro, because this is a phase shift of interferometric images. So each pixel has a height information. Therefore, it's easy from here to reconstruct this one. So new one appears. So if you look at the crystal surface, you can measure the nucleation rate and also the velocity of steps, no problem. So that is what we teach. By the way, this is the height difference, 5.6 nanometer. So this is one monomolecular height of lysozyme crystal. So let's go to the another one. So this is collaboration work with Juan, and this method is very sensitive, 100 times more sensitive than the other interferometer. Therefore, this is me, 10 meter long, very good, long, big crystal. So, and Alexander measured the growth rates of this one. It is 10 to the minus 5 nanometer per second. This is very small. So, for instance, here is a crystal. The crystal grow by the accumulation of monomolecular layer gradually. So one step higher, 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 higher. But you know, in this case, it takes 2 or 3 hours for one layer to cover the surface. Very slow, very slow. So we say this is the title is ultra slow growth rate of giant chip crystal. So this is probably this is the world record. Nobody measured this one. So for instance, today you have a rain. So if you have a rain, you have to drive a car. So the glass window will becomes wet. So in that case, glass window is dissolved. The dissolution rate of that one is 10 to the minus 4 nanometer per second. So if you drive your car in the rain for 100 years, the window completely dissolved. So that is very slow dissolution rate. But this is one order slower than that one. So it takes 1 million years, we said, conclusion, to have 10 meter long. So the 1 million years has some meaning because the lifetime of one volcano is this one, about this one. So you needed very constant heat source. That is a magma chamber just below the volcano. So the lifetime of volcano is 1 million years. That is in average. So the continuous heat was supplied from the magma chamber in this year. So it's also a nice work. And okay. So up to now, I mentioned about optical microscope, still very powerful, not only to see the surface, but also to measure the growth rate, very slow growth rate. And but sometimes we wanted to see the surface in larger magnification. So this one, atomic force microscope, AFM. Normally, we have contact mode or that kind, very simplified one, or you can scan on the surface. But we have frequency modulated mode. We say FM mode. So this means the one advantage is, so the tip is close to the surface, but here a little bit away from here. Therefore, you can get the structure of the solution leakage in between tip and the crystal surface. But here it is impossible because it's too very close to the surface. So, for instance, you can see the result. So this is by conventional method from calcite, calcium carbonate. This is our result. So this is calcium atom. So this is atomic resolution. In the solution, during crystal growth, you can see this surface. And but here you cannot say where is atoms and so it's a difference. So we apply that method to the understanding of polymorph calcium carbonate. Amorphous, laterite, aragonite, different phases. So but we are interested in this one, calcite crystal surface. Many people observed growth steps, for instance, like this. You can see some steps very clear. But another polymorph, aragonite. Some people, only a few people observed dissolution steps on aragonite. But nobody observed the growth step. I could not understand why it is so, because aragonite is also very popular crystal. But nobody observed this kind of clear patterns, steps on the surface. So we started why. That is my question. So some students studied this one. So I'm sorry. This is a very difference. We use FM-AFM, frequency modulated FM. So but the previous normal one is amplitude modulation. So we give some vibration, constant vibration. If here is one atom, then vibration mode will be changed in this way. So this is, FM radio is much clearer than AM radio. So this is a difference. So we use this kind of FM mode. So for instance, it's already, maybe we published one result, one of the paper about this one. But again, very important. So this is the surface of calcite. So this is calcium atoms. You can see there. This is 1 nanometer. So very high magnification. So if you wait the 8 seconds, you can get here the same, but this part is something different. So after 8 seconds, so the surface covered with completely different one. So this is from the diffraction. You can say this part was aragonite. This part is calcite. So at the beginning we thought, oh, here is aragonite layer. So they started to grow and cover on the calcite surface. But it was not so. It was not so. I repeat this one. So here is calcite surface. So I thought at the beginning, so new aragonite layer coming over, come over this surface. But it is not so, because the height, here is no height difference at all. No height difference at all. So this means the surface, only the surface structure changed. So a kind of phase transition of two-dimensional nucleation appears. So therefore, we say, so this is our speculation, the result, conclusion. Aragonite might be formed only via two-dimensional phase transition of topmost layer of calcite. So first you need calcite layer. Then there is a two-dimensional phase transition forming aragonite structure. If there is a aragonite structure in two-dimensional, then you get the aragonite three-dimensional structure. So we took a section from this crystal, observed by electron microscope. It was, this part was aragonite, this part was calcite. So probably this is the reason why we have no observation of aragonite growth steps. But once aragonite structure is formed, dissolution is easy. So you can see dissolution steps. So this is our speculation, but we need to study a little bit more about this one. Okay. So this is sorry, a little bit more higher magnification. This is during dissolution of calcite surface. This is small H pitch dissolving and taken by high-speed FM-AFM. So this is very high speed, therefore about, I heard 10 frames per second is very possible. Normally it takes 10 seconds to have one frame. But here you can get 10 frames. That is thanks to the laboratory of Kanazawa University. So Miyata did this kind of observation. So we can get some zigzag structure on this surface of calcite. So this is a low magnification. This is 100 nanometer. So we are looking at this area. Steps, dissolution steps are going back, reiterated. So if you look at this one, this is 2 nanometer. And the steps are going back from here to there, go up. So this was very strange because I can stop something. So this is calcite surface. This is also calcite surface. But what is this one? What is this? This is calcite part. One step down, we expected next to calcite steps, there is another flat surface of calcite. But it is not so. So if you take a section, you get this profile from here. So this is this, and this corresponds to lower steps. But in between flat layer, you have intermediate stage. So this is very much surprising because this is 0.1 nanometer. So one molecule of calcite molecule can be stored in here. But here, this is too small for calcite molecule. So what is this one? So so we did a lot of work on this one. And we did some simulation. We made nearly 10 models. And somebody in Europe did some simulation. Then finally, we get one conclusion. So this is an intermediate state. So this is calcite, CaCO3. This is CaOH2, metastable phase. So the lifetime of this one is very short. So steps as returning, coming back, then it's go. But still, you have sometimes until this layer dissolve. So in a sense, the more than 10 seconds, this intermediate layer is stable. So we have some models, and but I have no time. But finally, we come to a conclusion. So intermediate layer must be calcium, this one, frontline. So this is calcite, upper terrace of calcite. This is lower terrace of calcite. And this is transition risk. So it's easy to say, maybe this one, but you need to verify this model. So by what? By looking at this layer, water layer, whether from the simulation, we can see some cloud, you can see some cloud layer, water hydrated layer present on top of calcite surface. But you can compare the height here. Here is another next one. Oh, this is yeah. So MD simulations. This is calcite steps. This is lower part of calcite. So you can see this here is a model, calcium oxalate, OH. How to, I don't know English name.
Calcium hydroxide.
Ortholandite. So this is a simulation from water density. So this is on top of the surface. This is on top of the lower part. You can see this thick. But here you can see if you use this model, the previous model, the height of this height is the same. Only in this case. And therefore, so first I would like to show how we can get structure. This one is from the crystal surface, and as I mentioned. But after scanning, this is a water hydrate structure. You have some structures. They're very close to the surface, the first layer. So depend on solution conditions, chemistry, you have second one, and the third one, and the fourth one. And so if you, in this case, you added peptides. Sometimes we added magnesium ions to the solutions. In that case, this structure is different. And I have no time, but the water structure is independent of the structure of lower part, calcite. So water structure is a body center structure. This is body center. But the calcite is something different from body center. Anyhow, so they're using this one. This is the surface as you saw the movie. So this is the first terrace. This is intermediate layer. This is the lower part of calcite. So if you look from the top, this is simulation. You can get some stable calcite layer. This is a stable calcite layer. But in between this one, you have some complicated one. This is a CaOH2. So in order to, if you get average, look from this side, you can get average structure. This is top surface, this is lower surface. So if you see the structure or the thickness of water molecules, you have the same height here. This is one step lower. So only previous model could show this layer. This is one of the verification. So this is their image. So for instance, you can see this height is same as this one. And this is lower. But it's a little bit complicated. So if you look at the crystal surface, the very interesting point is another interesting point is this must be very unstable. But why this layer does not disappear immediately after dissolution? So this is our conclusion is due to this water structure, some structure water jacket. So this is one thing we could use some very advanced atomic force microscope. That was invented by Professor Yamada and some other co-workers. And they did a lot of work on that one. We just borrowed the equipment and then we got previous results. But now this is different topics. As I told you, the Japanese small satellite went to a small planet. So then they pick up some small crystals. I was interested in that one. This one. So small satellite landed on a small planet, asteroid. So after that, they pick up some small samples, mainly suns or some fragment of rocks. So we have that one. So this was already very primitive one was published, and this is about 5 millimeter in diameter. So we get this one. So from here we pick up small sample. Then we use FM to see the whole surface. And if you look at this one, the reason to look at the surface, as I told you, the crystal surface, a lot of information about the growth history. So we wanted to understand what's the history. History means when it was made or how first it did grow or when at what temperature they are formed. So the surface contains that kind of information. So this crystal is below tight FES. So okay. So I spent almost 3 days to look at this one. So small crystal was picked up with the help of small manipulator. Then place this one to the sample holder of FM, and then many times we failed, and finally we found steps. Here, for instance, you can get growth steps. If it is dissolution, dissolved steps, you can get rounded one, but this is very sharp, and the shape is related. The angle can be explained from crystal structure of FES. And here some spiral patterns you get. So this is very important because if you measure the step spacing, the not so exact one, and you can calculate growth rate and how long it took to form this crystal. Normally, that is, people said, oh, it took many years or many months, many days. But so whether it is so or not, you can see later. And the principle is very simple. So this is spiral growth steps, as you saw in the previous slide. So already more than 70 years ago, Frank mentioned about this relation. So step spacing is 90 RC radius of critical radius. So RC is this one. So the very important thing is, so we want to understand driving force, supersaturation. We want to understand, we want to get the information. And we can measure this one. This is molecular volume, so easy. And also, therefore, we need gamma, that is interfacial energy. So this could be obtained from solubility calculation. So Dr. Sato did a lot of calculation to measure the calculation, to measure the solubility. And So this is solidity, and this against temperature. So about this value. So if you plot this value to this plot, this is very famous plot zonal. The many crystals could be plotted along this line. So this is important concentration. This is surface energy or interfacial energy between liquid and crystal. So for instance, this very good soluble crystal like KCl or NaCl, they comes to this point. And this is difficult, calcium carbonate, maybe somewhere around here. But this crystal pyrrhotite is much less. From this line, we get the surface energy must be something like this, 150 millijoule per square feet, something like that. So we can use this one. And about we needed to just not here. So this one is. So this is very simple expression of growth rate. The beta kinetic coefficients times some concentration or supersaturation. So this value we don't know for the crystal growth. But roughly speaking, this dissolution kinetic coefficient can be we can assume this is very close to this one. Of course, this is a little bit smaller than kinetic coefficients for crystal growth, but the order is okay. So we cannot measure the growth rate when the crystal was grown by 4.6 billion years ago. But we can dissolve that crystal in water. In water, this is 0, and then from here you get this one, simple. So taking this one, and the equilibrium concentration is this one. Then we get the value of beta. This must be very similar one, 10 to the minus 6, 10 to the minus 6. And from the step spacing, we could measure the supersaturation. So this is 0.1 means 10%. This is larger high. And we get calculation. This is 1 micrometer per day. So the size of pyrrhotite, this crystal is about 10 micron or 20 micron, but the thickness is much smaller. So in this case, this pyrrhotite crystal could grow in less than 1 day. So in 1 day, that crystal grown, and it was stable for 4.6 billion years ago. Nothing happens because we can see the surface. Because the surface was so clear, no effect of dissolution, no contamination. So from isotope measurement, solution temperature was 25 degrees, we knew, and also the age also knows. So from looking at the crystal surface, you can calculate this kind of thing. Very quickly, crystal was grown, and nothing happened. This kind of growth history can be obtained from the surface. So I would like to thank you for many people. Not only these people, but also the other people. And the name is here. And Peter Victor suggested me to use dissolution beta for dissolution is nearly equal to the beta for growth. So that is his suggestion. So thank you very much. And so this is in Sendai. Please come to Sendai.
Thank you very much, Katsuo. Wonderful. Yes. Questions? It's a very tricky, all this investigation that you have performed. Very this one, the last one is Ryogu, how do you say? Ryugu asteroid. It has, was a very tiny sample from space, from asteroid, and then this is this paper is fantastic. It's amazing because what is the size of the sample that you brought from space?
Yeah, I got 3 millimeter or 4 millimeter.
3 millimeter, but the sample that brought from the whole mission.
I think in this volume there are many. So the first one was not so successful.
Yeah,
they got on this tiny one. This time, a lot of this size.
Yeah.
Sometimes 1 centimeter, I guess. That kind of block.
And then you brought just some millimeter. Right?
And then to pick up the original surface. So it's not so easy. We know this is original surface, but to convince other people, this must be the growth step. This is not so easy. So this is... Yes.
And then, you think that this crystal was grown at the beginning, maybe at the time. I mean, 3 point. You say how much? How much? Any years ago?
4.6 billion.
4.6 is the solar system origin.
Beginning of solar system.
Solar system origin. So this is,
So in a small planet, not a planet, maybe 100 meter in diameter, they have some water or ice. So when the ice dissolved, the sun is here, they come here. In this case, ice will be dissolved and they form this kind of things.
And this is carbonaceous.
Fe.
Carbonaceous
SFES.
Yeah. Okay. And in the case of calcium carbonate, calcium crystals. So it's fantastic the resolution that you are able to obtain with this. This is really, so it's molecular, atomic resolution, right? But which is the unit of aggregation that you have? Is this calcium carbonate? Because you have a transition phase there, which is calcium hydroxide, right? I don't understand how this happens at molecular stage.
So probably this is calcium OH2, COH2. So,
but where did the carbonate came from? I mean, this is you have calcium hydroxide there.
Just wait.
How you?
Yeah. So the proton was released to form this one, and this is aggregate of this one. So they release the surface, they leave the surface, and then in the solution you have CO2. So this is the reaction.
Oh, I see.
Dissolving water to form temporary this one. Then finally you get the stable CO2 and this one. This is our model, and we did simulation based on this model. This is a very good agreement, and probably they spent. I did not do it, but Miyata, Professor Miyata, he did a lot of work, and he spent more than 1 year to think out very complicated. Why the step is so small? This is too small for 1 molecule of calcium carbonate. So, so therefore they thought this must be the intermediate.
To me, I wonder about the quality of the image. Who took this image? This is
in Canada.
Araki or no?
No, Araki. No, of course she can do it, but her colleagues in Kanazawa University. Yeah, that's university is very nice, and they have the laboratory. No, nearly 20 or 30 AFM. Every student.
20 to 30 AFM?
Yeah, because they make them by themselves. Oh. So therefore, it's easy. So we want to get the information about the Z deviation. Then they change, oh, it's okay. So if you buy commercial one, it's not so easy. But I forget to tell you, and the AFM is very high resolution. It's okay. But it's very weak to measure the growth rate Z direction. Because if you change the condition, so machine equipment itself move. So therefore, the position of the cantilever is not always reflect the dissolution or growth rate. But contrary to AFM, but in the case of optical interferometry, you have standard area. So reference, you have reference. This reference is fixed, does not grow. This crystal, this area, this crystal grow. Therefore, if you measure from here to here, from here, this is a reference. Then you can get real dissolution rate or growth rate. Okay. So the optical interferometer is very strong to measure the vertical Z direction. But the FM is very good for getting X, Y directions. So you need to
combine. Yes, please.
From a very chemical instinct, I think that you must have more water there. I think that that species in the intermediate are very hard to exist without more water. And therefore, I cannot prove it, but
you mean that
that requires at least to stabilize that bicarbonate of a lower water molecule.
Yeah, and we got the same questions from others, and therefore we studied how long, why this is stable for sometimes. You said that this is very unstable.
It's hard to live without water.
Therefore, we have water jacket on top of this. Structure hydrated layer will prevent for this molecule to leave the surface. That is our conclusion, not the proof, but at this moment, that is conclusion. Because because of we had the same question before. The height of this one. So this height can be obtained in this simulation only using that model.
Using what?
Using previous model.
Okay.
So if you use another model, this thickness becomes half. That is one of the side evidence. We need more evidence. That as far as we could see, that is still not so easy to get this image.
Okay.
In fact, that species is conventional. That monohydroxide of calcium is conventional. It's a pure stoichiometric. I think that it must be a part, a very transient situation.
Yeah, transit. I agree with you completely. So, so I wonder whether there is another way to check it. So of course you can use X-ray, low angle, like the Elias Frick in the Netherlands did it. He measured. He get the diffraction only from the surface. But that is average. But we can choose that point, step front. So as long as there is no other method, we have to continue this kind of work.
But with X-ray diffraction,
It's average.
but I mean, what is the lifetime of this transition there? If the lifetime is, small, then short will be impossible to detect.
Simulation that 20 nanoseconds or something like that.
Pardon, say?
20 nanoseconds or something.
By X-ray diffraction, I don't know.
Perhaps.
And also, this is very small. So the crystal surface is from here to here. The width of this one is only this one. So whether you get the reasonable power of diffraction from this situation. So therefore, we needed to see. We can choose this area. That can be done only by this method at this moment. So, yeah, you are very right. We want to understand more. That is very true.
More questions?
So for younger people, you are welcome. And if I look at your face, she is young, he's a little bit old, and maybe he's intermediate. So that kind of information you can get. It's the same as a crystal. If you look at the crystal, you can get this is old. This must be grown very fast. But normally they crush and they dissolve and analyze chemistry. So, but it's very pity because surface contains a lot of information. So if you have a reasonable good tools, you can review the history of the crystal, even in such small scale or even in ancient times.
Excellent. Okay, so Katsuo, thank you very much for your talk, for your lecture, and for your contribution to so many years to the field of crystal growth. Thank you.
No problem.